Let's discuss the odd-numbered nuclei in more detail. Odd-numbered nuclei are interesting because the chains are usually longer due to the odd number of protons or neutrons in the nucleus, which inhibits spontaneous fission. A typical example is neptunium-237 and calcium-48, which gives us element 113, resulting in 4 decays followed by spontaneous fission. In 2003, americium-243 and calcium-48 was used instead of neptunium, thus moving 1 step higher and 2 neutrons to the right, giving us 5 decays and then spontaneous fission. It would be nice if we take element 117 with calcium-48. This experiment was done in 2010, where 6 alpha decays were followed by spontaneous fission, which looks like this. Indeed, this is what they look like. This is neptunium-237 plus calcium-48. This is americium-243 with calcium-48, a 4n decay with 5 alpha transitions followed by spontaneous fission. Also, a 3n decay with 5 alpha transitions and then spontaneous fission. And finally, berkelium-249 and calcium-48, where we have 6 alpha transitions before spontaneous fission. The number of events is shown here. We have 2 such events, 3 such events, 73 such events, and so on. These decays were observed in Japan. 3 decays in 9 years. This is it. Its lifetimes are shown here. 1.4 milliseconds was the first decay, while the rest are measured in tens of milliseconds, seconds, and tens of seconds. In order to verify our results, our chemists proposed an interesting experiment, which was based on the assumption that, if everything is correct, then the periodic table is arranged in such a way that when we arrive at element 89, a whole set of actinides, ranging from 89 to 103, is to be removed. They all have the same chemical properties, and we return to the law of periodicity by considering elements 104, 105, 106, and so on. When we use element 115, we have 5 alpha decays and then spontaneous fission of the 105th and maybe the 104th elements. The spontaneous fission trail takes place after the actinides. Therefore, if we remove lanthanides with actinides from the reaction products, then we remove the entire background. And radium and francium do not split spontaneously. Therefore, knowing that we have a long-lived nucleus, which is obtained as a result of 5 decays of alpha particles belonging to elements 104 and 105, it must be outside these nuclei, that is, it must be a transactinide, not an actinide, but a transactinide. It was important that such an experiment was carried out. After removing all actinides and thereby removing the background, elements 104 and 105 became visible, the properties of which were exactly the same as those in the decay chain when spontaneous fission occurred. And here it is, the decay chain. It represents 5 consecutive alpha transitions, which take about 20 seconds, and then nothing further. And only after 23 hours does spontaneous fission take place. Here we are talking about this spontaneous fission. I would like to mention that we are not very sure that spontaneous fission really refers to the isotope dubnium-268 of element 105, because this element and this isotope have an electron capture period of about 24 hours. Therefore, it is very likely that it is actually experiencing electron capture. The isotope Rutherfordium-268 passes from odd-odd to even, which lives for only 1 second and then divides spontaneously. This pair is responsible for the spontaneous fission at the end of the chain, and this pair, dubnium and rutherfordium, are transactinides. Therefore, the status that chemists proclaimed produces transactinides works regardless of how they decay. After long-term irradiation of americium-243 with calcium-48, the stationary catcher, which does not rotate and is cooled by water, covers all recoil nuclei emitted from the target, which is irradiated for about 1 or 2 days. After that, it is removed, and fractions of chemical transactinides are released from it, while all actinides are discarded. This is a fairly reliable method in radiochemistry, where purification is calculated in 4 to 5 orders of magnitude, maybe even 6 orders of magnitude. After that, the thinnest possible target is made from these chemical fractions, which are then placed in such a way between 2 detectors that if spontaneous fission occurs, both fragments are visible. They exit in different directions. Niobium and tantalum, which are homologs of dubnium, are used as carriers. Therefore, this isolation can be done rather reliably. We have 5 such chambers, and they are placed in a neutron detector, which is a neutron moderator, in which there are 78 helium-3 neutron detectors, so that the whole system has an efficiency of about 40% and can register the number of emitted neutrons. We saw that these fragments significantly exceed the expected amount of energy. For example, for uranium, fission is not asymmetric but symmetric. We also saw that, despite such a high energy, 4.2 neutrons are still emitted in each fission window. Now we can compare the data obtained by the separator. Here are the decays, and then spontaneous fission takes place, which is now obtained by the offline technique. We see that here it was the end of the decay chain of the nuclei with atomic number 115, right here with atomic number 105. The same amount of beam energy was used for both experiments. The dose is also more or less the same, but since we used a thicker target here, 15 events were observed here. The cross-sections coincide, the half-lives are within the statistical parameters too. The kinetic energy of the fragments also coincide, and the number of neutrons is 4.2. Now we can plot a graph. These are the fusion reactions of lead and bismuth target nuclei. These are the actinide target nuclei fusion reactions with calcium-48. Now, if we look at the spectra of alpha particles of odd-numbered nuclei, we will see different results from that which was from even-numbered nuclei. Even though we are close to the shell, this is the resolution. But here we clearly see a group that is located completely outside the parameters of this resolution. As we move from a large atomic number to a small one, and as we move from a spherical nucleus to a deformed nucleus, our spectrum expands. Here it can be seen even more clearly, as well as here and here. This indicates excellent material for investigating the excited states of super-heavy nuclei. Transitions to these states are interesting because if they are measured accurately, then they can be drawn and the probability of their location can be depicted. And this, of course, broadens the scope for theorists, since they usually only calculate the ground states. But here, they can also calculate the excited states of nuclei. This roughly indicates where we are according to these elements. Now, 3 more elements will be named. And now we will speak about their half-lives. Experiments with calcium-48 will make it possible to produce nuclei with more than 165 neutrons. Look how, as soon as we move in this direction, the half-lives rise sharply. For example, for the isotopes of element 111, it increases by 5 orders of magnitude. Well, the same goes for the 110th element, and the same for the 112th element. In general, moving towards this region is always associated with a sharp rise. This is such a dramatic rise that we go beyond the region of about 1 second. And in the range from 1 second to 1 minute, we are already able to study the chemical properties of these elements, which was not possible before. I would also like to mention that all of the isotopes that I have spoken about, except for the 118th, were confirmed in other laboratories and other facilities, about 7 to 8 years after it had been done here. And that is how the experiments that were completed in Dubna were confirmed.